Good morning. Oh, now you can hear me. My name is James Croall. I am Director of Product Management at Coverity. I've been at Coverity about 8 years, so helping our customers, but not just paying customers, but also open source users, adopt static analysis and automate their testing, really making it part of their culture, their day-to-day development practices. I am a developer at heart. Prior to joining Coverity, I spent about 10 years as a C and C++ and Java developer. I still keep my hands dirty. I use our own tools. I use FindBugs. I'm still writing code. I do some prototyping of new features. I even write some custom static analysis checkers for our customers. So today's going to be a technical discussion. What I'd like to do is share with you a little bit about the evolution of static analysis, kind of how it began a long time ago, maybe we'll say back in the 70s, how far it's come over the years, and we'll take a look at some real open source projects. We'll actually open up their code and take a look at some of the defects that they've found and fixed using modern static analysis. So I think you'll see that this is really not your grandfather's static analysis. This has come a long way, and it's become really a very trustworthy extra set of eyes when we do our development. So static analysis, I think everybody that's come by the booth already knows what static analysis is, but just to be clear, static analysis is by definition the analysis of a program without actually executing it, right? Looking at it while it's at rest. So specifically what we do is we take the application's source code and we use that to uncover potential defects without ever running any test cases or even running it manually. This isn't new. I mean, this is ancient technology at heart. If I had to draw a timeline, I would probably start in the early 70s with the first C compiler, although it probably dates back before that. Now, I'm certainly not old enough to have used the original C code linter, but I do actually have some experience with it. In my first professional job, I inherited a small little C program, and this much older than myself original author was very clever. He set up the makefile so that it would run lint, and if lint reported any warnings, it would exit 1. So right, it would terminate the build. It would fail. This just annoyed me. I saw all these warnings. None of them looked very useful. It was like implicit cast this, or maybe I don't think I ever had an extra semicolon, but it was really silly looking stuff like that. So what did I do? I just hash marked out that line from the makefile. So I commented it out, and I went on with my business. And I'm still skeptical to this day that if I had actually used lint, I would have saved any time. Right? My code might have been a little more correct, but would I have really gotten anything out of that? So I think a lot of people have had a similar experience with static analysis at some point. Just reports a lot of, yeah, that's wrong, it's smelly code, but do I really need to fix it? Let's see, from the 70s to, this is kind of arbitrary, but I see a big gap between sort of the 70s and mid-90s. Right? We didn't see any big quantum leaps or even some small leaps in static analysis. In fact, most of our testing was just unit testing, QA testing, manual testing, the traditional methods. But once we got to about the mid to late 90s, we did start to see static analysis start to evolve again. Right? We have FindBugs. We have, actually FindBugs is a great example. Static analysis has moved from simple pattern matching, like looking for missing semicolons, to these little mini programs that can actually look at and reason about the code and decide that something's wrong. So it becomes a little more intelligent, can find more complex issues. But at the same time, there's still some limitations there. We've made a big leap. We're not reporting as much noise, but we're not looking very deeply at the code. So enter, let's say, early, mid-2000s, where static analysis has really taken off even as a commercial solution. There's a lot of tools in both the open source, free, and in the commercial market today. I mean, in Java, we've got FindBugs, Checkstyle, PMD, lots of add-ons for those. In the commercial world, we have Coverity, of course. We have Fortify. We have AppScan. I think I've seen a couple other products that I even just learned about today on the floor this week. And there's actually a lot of innovation happening here. Static analysis is really moving forward. The way I would characterize a modern static analysis, firstly, is kind of a holistic view. Instead of just looking at a single file, we're looking at the entire program. So we can find defects that cross very complex call change or data flow paths. We've also come a long way in understanding how real-world code is written. Right? We recognize that it's not enough just to report that something is out of place, but maybe it's out of place for a reason. Maybe there's a common design pattern or idiom that calls for that to look out of place. Right? So we have to start to build that understanding of real-world code into the analysis and make it smarter so you don't get a lot of noise. So we're all Java developers here, I hope. And for Java, we have a lot of options. Right, we've got, I think everybody that's come by the booth, I'm kind of joking when I ask, do you use FindBugs? Because almost everybody's already using FindBugs. We've got PMD, we've got checkstyle, we've got Sonar. There's probably a lot of other tools that I'm not mentioning here. We also have, of course, Coverity. They all do different things. They're not even necessarily one or another. Some of these tools are quite complementary. And when we're looking at adopting a new tool, right, trying to improve the quality of our code, we have to ask ourselves a lot of questions. First is, does it find defects that matter to me? Right, some tools might find coding rules that just don't apply to my code base, for example. What is the false positive rate? Right? Is it going to waste my time? Does it fit into the way I already do my development? Does it have IDE plugins? Does it give me the reports I need? Does it fit into Jenkins? And another issue that's actually I find often neglected is, does it offer persistency? Like once I've found an issue, does it remember that issue? Does it track it over time? If I mark it as a false positive or noise, is it going to bother me again? Is it going to bother my peers? All right, so these are all attributes that we have to look at when weighing which static analysis tool to adopt. So what I'd like to do, to give you some concrete examples of how far static analysis has come, is walk you through some real-life defects that open source Java applications have fixed over the last, it's about 2 years that they've been using our own solution in the cloud. The defects that we're going to look at were all found by our free for open source solution. So this is free as in beer. If you have an open source licensed project, Coverity is free for use in the cloud. Let's see. And so what I'd like to do is just introduce you to what is Coverity Scan, and then we're going to get into some actual code, which hopefully is the most interesting part of the story. So Coverity Scan goes all the way back to some academic research that we did at Stanford University in the year 2000. This started as an academic research project only analyzing C and C++ code, and one of our first test subjects was the Linux kernel. Right? I mean, if you're going to pick a complex C application, that's a great one to start with. In 2006, with funding from the American Department of Homeland Security, we launched this project called Coverity Scan. The goal was to improve the state of quality and security in all of these open source packages that not just the US, but the whole world really relies on day to day. So this ran for a few years, and then budget ended in 2009. But as a company, we've decided to stay committed to this project. This is both sort of a bit of goodwill. It actually helps us improve our free and commercial product. Right? The more code we look at, the more we learn what people are doing, how code is actually written, what are the common design patterns and idioms. Helps us tune out false positives, helps us get better. And plus, you know what? Let's be honest, it's also a great marketing tool for us. Since the launch of Scan, let's see, these stats are probably out of date already. We have over 2,000 open source projects participating. That's a mix of C, C++, and Java. I think the majority is C and C++ because that's how we got started. And to date, actually just in the last year alone, these projects fixed over 50,000 defects. These are defects that could have caused a crash, could have caused very commonly unpredictable behavior. Often these logical errors just lead to the program doing the wrong thing. Even security vulnerabilities. We've found a number of what have turned out after they've been fixed to be potential causes of zero-day privilege escalation exploits, for example, in the Linux kernel, as well as some web security vulnerabilities in popular Java applications and application frameworks. So I'd like to shift gears some slides for a second and just show you what is Coverity Scan. Coverity Scan, it's super easy to remember this site, scan.coverity.com. When we come to Coverity Scan, hopefully it's pretty welcoming. You can sign up for free. But what I'd like to do is take a look at the projects that are using Scan. Let's see, there's thousands of projects here. What I'd like to do is just search by Java. Let's see how many we have. I think there's pages upon pages of most of these projects. If they have lines of code listed, that means that they're using Scan today. We've actually looked at their code. We're reporting them defects. They're doing something with it. Some of these guys, though, they're just pending. That means they've just gotten started. Let's see, let me pull up Hadoop. So I think Apache Hadoop has been using Coverity for about 10 months, almost a year. Let's see. All right, so they joined in August of last year. Actually, it looks like they just submitted their last build about less than a day ago. So just as a guest, I don't have any special access. Like I can't actually see what they've been doing. This is really for security purposes because some of the defects we report, if you actually looked at the bug, it could be the root cause of a security weakness. It could be something exploitable. So in order to see defects, you do have to actually request access. That will go to the project maintainer. But they're usually pretty open. I mean, if you're involved in the project, you can usually get access. If you have your own project, and you have to be involved in the project, this can't just be, oh, I downloaded Hadoop and I want to see what defects are in it. You can sign up. Oops, that's the wrong link. When you sign up, you can either, if your project is already in GitHub, you can just sign in with your GitHub credentials. We can actually pull the source code automatically, run the build, everything is integrated. Or if you have a project somewhere else, you sign up manually, right? Username, password. You can imagine how this goes. So that's just what is Coverity Scan, how to get to it. Let's see, I think what I have next, I'd like to share with you a little bit about how it works. We'll talk about 2 projects that have been very successful, and then we'll get to the source code. The way Scan works is once you sign up and register a project, we give you an option to download a special Coverity build utility. This is a really universal adapter. It works with any command line build, whether it's Ant, Maven, Gradle, you name it. It's really transparent. It works under the hood to intercept system calls and detect the compilation, and then runs the Coverity analysis. So what you do is you download the build utility. It's not an exciting demo, otherwise I'd show you. You download the build utility, you run your build. What that does is that captures all of your source code and dependencies, everything we need to analyze, and then that uploads that to the cloud. In the cloud, we run the analysis, we give you a list of results, and you get an email back when they're ready. It's actually pretty straightforward. A quick case study on Linux. So I realize this is a C project, and you guys are all Java developers, but bear with me, we'll get to Java. Linux was, again, really one of our first users. They began as a test subject all the way back in 2000 as academic research. And to date, we have detected almost 20,000 defects in the kernel, and they've actually fixed almost 10,000 of these issues. Again, these are all crash-causing resource leaks, race conditions, really gnarly stuff. One thing that's interesting here is you can see how they've actually helped us improve over the years. We started with what I think is a pretty respectable 20% false positive rate. That means maybe 8 out of 10 defects is real. That's actually pretty good for static analysis. But we've improved both through feedback from the Linux developers and also just our own review of their findings to less than 10%. So we find this is really a sweet spot. If 9 out of 10 defects is real, then hey, almost everything is worth looking at. It might not cause a crash in your program today, but it is, definitionally, it's incorrect code. Right? There is something wrong. It could be a problem today. It could be a problem tomorrow. You can also see we've gone from detecting barely 1,000 defects to lots, many thousand defects. In just last year, Red Hat's Dave Jones took over ownership of managing the Linux Coverity experience. What they did is they shifted to a scheduled weekly build. So every week we run the latest version of the Linux kernel. We integrate with Git, with the Linux Git repository, to say, okay, we found a new bug. Let's look at the Git change history. Let's figure out who introduced that bug. And then we send them an email. So within a week of introducing a new defect, the guy who's to blame gets an email. Hopefully he can fix it. Now, in an ideal world, we would have, of course, real-time feedback. But the fact is, this is a free service. We have limited CPU cycles today. We can afford to run the Linux kernel about once a week. The false positive rate, thanks actually to Dave and doing some tuning, he's brought it down to about 8%. So really everything we report in the Linux kernel is worth looking at. Really good stuff. They've been very happy with this. But let's shift gears to Java, because we're all Java developers here. What I've got here is a breakdown of the top 10 most fixed issues in our Coverity Scan service. So this is actually a combination of FindBugs and Coverity. What we do is, because FindBugs is just so ubiquitous in the Java community, we automate and manage the defects for both FindBugs and Coverity issues, because it's all worth fixing. But what's interesting is the #1 most fixed issue that our users have chosen to fix are just classic null pointer dereferences, or, well, null object references. So in Java, obviously, this doesn't cause a seg fault, right? But this will cause, in most applications, some undesirable behavior, right? Whether it's just some exception being thrown in some application log somewhere, or maybe that bubbles up and causes an unexpected dialogue to the user. Now, my favorite checker category, defect type, actually my least favorite defect type are concurrency defects. That's these concurrent data access violations, right? The idea where I have some data that should be synchronized, except when I forget to synchronize around it. Java makes concurrency, and in fact, there have been some talks this week, I think, on concurrent programming in Java. Java continues to make concurrent programming even easier, or in my opinion, seem easier. I mean, there's still a lot of ways you can shoot yourself in the foot or blast a finger off with race conditions or deadlocks, or thinking that you have an atomic operation and it really isn't fully atomic. So these are, as far as the Coverity found issues, right, that's the #2. These are very high impact defects. So what our users are telling us is that the null pointer dereferences, the concurrency, and even the resource leaks are their #1 or their top most fixed defects. Actually, security is not on this list. We recently opened up our OWASP top 10, our web security checkers to these users. I expect that to quickly bubble up, hopefully, to the top of the list. The impact of a SQL injection or a malicious code injection is probably pretty serious compared to some of these. If we double-click on Hadoop, now, so I didn't have the stats in the web UI, but I'm going to give you a look at what they've done. Hadoop HBase is pretty well known. This is, I think, the database backend behind Hadoop. They've been using Coverity again since about 2013, about a year. We've run both Coverity and FindBugs for them, and of all the defects we found, what's interesting is out of the 450 or so Coverity issues, they've already fixed almost 50%, actually 41%. I'll round up to 50. Of the 300 FindBugs issues, they've fixed about 20%. So what's interesting is they tell us they've been focusing on these crash-causing and significantly performance-impacting defects before they ever get to the dodgy code and the internationalization and the just general best practices. Of the Coverity issues, they have fixed all of the exceptional resource leaks. In most cases, these were, actually in all cases, these were leaks of system resources that cannot be automatically garbage collected and would have caused a progressive decline in the performance of the database backend. They've also fixed 100% of all detected program hang type defects. These are race conditions and other logical errors that will lead to a condition where that execution path just hangs. I think they've also fixed some all of the performance inefficiencies, but those are just very minor optimization issues. Okay, so that's all kind of theoretical at this point. What I'd like to do, since I'll bet all of you have seen what FindBugs reports, I would like to show you some actual bugs that these folks have fixed in their source code. And I'm going to try to do this with a live demo. We'll see how the internet works. Let's see. So the first project I have is, we'll start with something very basic. We'll look at a null exception in the Antler project, which is, I believe, a language parsing engine. So I'm going to have to sign in. Coverity.com. So I have permission, so I'll be able to view the defects. And I want the null exception. Here we go. So what this has done, this is logged into the web UI that all of our open source users get to access. I don't want Geneva, I want Antler v4. And I think that it's this one. Okay, here we go. Let me make this screen a little bigger. So what we are looking at is the actual Antler source code. Looks like this is in some serialization, some printing routine. What we're looking at is a null pointer dereference. In this defect type, we have an object that could be null. Actually, we're going to have evidence that it is null. And while it is null, we're going to use it. Right? What happened? That throws a null pointer exception. Here's the source code. What we do is we present the defect report as these, it's annotated in line with the code. The green tells us, shows us the exact path through all of the conditionals and loops and so on. So in this case, actually let's take a look at this line here. On line 115, we're comparing the G object to null. And it says we take the false branch. So that means that it's not null, so it's null. Make sense? And so we have evidence that the G object is null. And then on line 116, it says we're dereferencing it. But I don't see G being dereferenced anywhere here, right? What's happening is that G is actually being passed into another method call where it becomes dereferenced. And it's actually implicit, right? It's not being passed as a parameter, it's a field member. So what happens if I unroll this function call, and this method call could even be in another class. It doesn't have to be in the same file. In this case, I think it is in the same file. You can see indeed, down here on line 133, G is being used, throwing a null pointer exception that the developer didn't expect. So I've just thrown a lot of stuff out here. I'd like to actually pause and see if anybody has any questions or clarifications about what this is reporting, why this is a defect, anything at all, really. Or is it pretty clear? I see some nods. Okay. Well, boy, if we don't get any questions, this is going to end up being a short talk, so I welcome questions. So this is a very basic example. What this is highlighted is that the analysis is not limited to a single function. It's not even limited to a single class. In theory, this dereference could have been 10 levels deep on the call stack. I can also show you, this was actually a favorite of Terrence Parr, who was the self-described maniac or maintainer of the Antler project. We're going to look at a copy and paste error. It's a very simple type of defect, but it has a very profound impact, as you'll see. Oops, I was already there. I want copy and paste error. And I can't actually say what Terrence's reaction was, but I think he cursed up and down once the light bulb went on here. So in a copy and paste error, what's happened is it's very common to cut and paste code across your application. Maybe you have some boilerplate, but what this is going to tell us is that I've copy and pasted some code, changed the identifier maybe in some places, but there's a place where I've failed to rename a variable, change an identifier. So what we've got is you can just glance at this and see that these two blocks of code are very similar, right? If returns equals null, if locals equals null, our ret vals are locals, our ret vals are locals. This says though, ret vals AST equals returns, our locals AST equals returns. So the analysis says this looks like a copy and paste error because I probably should have said, let's see, our locals equals locals. All right, so it's to make it clear, returns, locals, this should be locals. So what's going to happen here is this application is simply going to do absolutely the wrong thing in this case. I am not familiar with this code. I don't know exactly what the impact would be. But when Terrence saw this, seriously, he swore up and down. This code is used behind the scenes by, this Antler is typically a software component that's used, I think it's used at Facebook, I think it's used pretty widely. So incorrect behavior lurking deep in the bowels is really not a good thing. Have any of you guys ever made this type of copy and paste? You forget to change a variable and then, I'll tell you, I've made this mistake. And then I go into testing, I spend sometimes I'm lucky, I catch it within 30 minutes, but sometimes I spend a whole day wondering, and then at the end of the day, wonder where my whole day went. It just went catching this typo. So quality issues are one thing. There's also been a lot of talk lately about security, right? We've had the heartbleed thing in C and C++. We had the Apple go-to-fail bug. I tend to believe that there are traditional security defects, like SQL injections and cross-site scriptings. But really, if you have any code that is security critical, for example, an authentication routine or making some authorization decision, maybe some role-based access, you should really treat any software defect as a potential vulnerability. I'll actually show you a good example here. I'm sure you guys saw this in the press, but I'm going to show it to you again because I think this is a really cool defect. We're actually going to look at a bit of C code here, but the same defect could really happen just as easily in Java code. Oh. Looks like the refresh. Here it goes. Did you guys all see the Apple go-to-fail bug? It has a great name, go-to-fail, like Apple fail. I'm sure some of you have seen it. I'll just talk about it anyway. The Apple go-to-fail bug, it was in C. Same thing, though, in theory, could happen in Java. What happened is it's basically a case of unreachable code. Now, Coverity is not unique in that we're the only tool that could find this. In fact, a lot of naive static analysis tools can find this. What's happening is we have this go-to right here, right? We're handling an error case, but it looks like the guy just has it twice. I know I'm a BI user. I've certainly had cases where I copy and paste one too many lines and end up with the same line repeated. Maybe that's what happened. I'm just speculating. Or maybe it was the NSA, who knows. So the go-to-fail here will always execute, completely skipping this security critical code. This is a case where if I just glance at this in my editor, I might not see it. I mean, it looks, sometimes you have a case where you look, it looks indented, so clearly it's right. It doesn't look obviously wrong at a glance. So this is a case where having an automated tool, an extra set of eyes, can really be quite helpful. I'm curious, just a show of hands, how many people, I know we're all Java developers, but how many are building web applications? Oh, wow. Looks about maybe 60%. One thing we've recently added to the scan service, which is, again, free for open source, is our web security detection. So we have a complete OWASP top 10 detection, and we've already been finding some great defects in open source. One that I'd like to show you is a SQL injection in an open source. It's kind of a defect tracking and aggregation system. They actually gave us some credit on their blog for finding this. Bear with me 1 second. I gotta pull up the. It was a SQL injection. I think it's the second one. Everybody understands the basics about SQL injection, maybe, I hope. SQL injection, well, I'll just explain what's happening here. This is a web application that's accepting user input. I'm not sure where the input's coming from, if it's from a form or from an API call. The point is, data comes in from outside the application, right, provided by a user or an attacker. And then what they're doing is they are manually constructing a SQL query, a database query. In this case, it's actually not JDBC or something. They're using Hibernate. But rather than using just the built-in mapping, they're constructing a specific query. What's happening is this hint, where is it? It's right here. I can actually go all the way back to the start. So it looks like retrieve by hint is receiving this hint, probably from the user input. And hint is being simply concatenated, literally Java string concatenated into this SQL query. The problem is, if this hint contained special SQL code, the user could actually modify the query and return. I don't think they could actually, in this case, like delete data from the database, but they could certainly manipulate the query and get out extra information. What's kind of interesting to me is that Any guys Hibernate programmers? Maybe, yeah. So some of you will see that they're clearly using named parameters in other cases. So why aren't they doing it here? Right, they're just concatenating the string. So in any case, we have identified this SQL injection. It's actually a HSQL injection if you want to be nitpicky. But because we are a tool by developers for developers, we understand that most developers are not security experts. In fact, these days, security is so complicated, it's really a full-time job to stay on top of all the fixes, all the weaknesses. So what we do for security is we're explaining step-by-step how to fix the problem. So that's what this little yellow box is all about. We say for Hibernate HSQL injection, you should probably just use a named parameter. For example, the colon hint. This is context aware, right? So if this was just a JDBC, we would explain how to use a prepared statement and the whole 9 yards. Does this make sense? Any questions or thoughts? Questions about maybe what we... No, great. Well, I have one more, and then maybe if you have any questions, I'd be happy to field those. Let's see. The last one I have to share with you was a malicious code injection in Apache Roller, which is a open source blogging platform. So I have to admit, the first time I heard OGNL, I had no idea what it was. I had to look it up. OGNL is kind of an add-on expression language. It's called the Object Graph Navigation Language that does nice little convenience things like allow you to get and set properties. It also, however, has the ability to execute arbitrary methods within your application. So you can imagine that could be very dangerous if you have a user on the outside able to just invoke arbitrary methods in your app. I mean, heaven forbid, even if you had access to that without a login, right? Anybody could execute anything in your app. That's exactly what we found here. In this case, we have this getter routine, get page title, that is receiving from the user, I think it's through an API call, the page title. The problem is this page title is going to be evaluated by this really clever OGNL engine, which has the ability to, based on the input string, execute arbitrary code. What makes this particular defect even worse is that there was a path to this, this weakness that wasn't even protected by any user authentication. So anybody could come to an Apache Roller installation and then invoke any method within Roller. So a pretty serious vulnerability. And in this case, I'm not familiar with what the author's intention was, but this is probably just a misunderstanding of what's possible with these APIs. All right, so again, another good reason to have this extra set of eyes kind of watching your back as you're writing your code, especially your security critical code. So I invite you, if you're doing any open source development at all, Coverity is free for use as long as it's an open source license. There's something that I'm not allowed to put into writing in a slide yet, but if you are doing commercial development, we are about to launch a kind of a freemium online service, kind of like GitHub, where you are able to sign up, submit code, get defects for free with some basic functionality. And then in the future, you'll be able to just put in a credit card number, very low price to add additional features. I'm not trying to make that sound like I'm selling anything. I just want to invite you to try out Coverity on your open source development. So any questions? Is there anything at all about the defects, about the projects we've worked with. Mm-hmm. Uh-huh. Mm-hmm. Yep. No, yeah. It's a good question. So let me repeat the question. The question is basically what sort of algorithms are we using in order to do this detection? Is it brute force? Like what's going on under the hood? So none of this there is of course some secret sauce, but there's a lot of stuff I can share. In short, this is not just like a single unified analysis algorithm. The engine is actually a family of, at this point, it's probably 30 different algorithms that look at the code in different ways to find different defects. That first one, that null pointer dereference, that interprocedural, what we do is we analyze the whole program. So what we do is we build a whole program call graph, right, which has maybe many entry points, top to bottom. And then what we do is we analyze it depth first. So by the time that we analyzed that function where the defect appears, we already understood what all of the called functions do. Does that make sense? So we see that this function is going to dereference one of its parameters. So, when we call that function, we know what happens. That's kind of the basics. There's a lot of other magic that goes into it. For the copy and paste, and again, I don't think this is a secret, but what we do is since we're analyzing the abstract syntax tree, we're actually able to take subtrees and compare them. And if they look, there is some secret sauce to what determines that trees are similar and different. But what we were able to do is we were able to remember those two functions. We say they look almost identical except for this one thing is out of place. Right? So that's how we're able to very efficiently identify a copy and paste error. And the list goes on. It's actually been quite educational for me. So I don't work on the analysis itself, but I've tinkered a bit. It's actually quite fascinating to see some of the clever techniques that go into efficient defect detection. Because it's one thing to brute force. It's another thing to come up with a clever algorithm to reliably and quickly find these defects. We actually have, if you're curious about the topic of static analysis on our website, it's a little bit buried, but we do have a number of white papers about some of the techniques that have been patented. We actually have about 15 or 16 patents on different static analysis techniques. It's some interesting reading. What jurisdiction are the servers in? So for our cloud services, let's start with Coverity Scan. Coverity Scan is hosted in the United States. It's on a combination of kind of co-located servers as well as Amazon Web Services. I don't think does that answer your question? Okay.
You talked about multi-class analysis.
Mm-hmm.
In Java, it's not uncommon to use dependency injection.
Good question.
Which means that sometimes it's difficult to work out what method you're actually calling.
Mm-hmm.
Do you support particular frameworks?
We do. So we do have specific support for Spring Framework and some other common and dependency injection frameworks where we will actually look at the application configuration file to infer these things. Now, it turns out, however, that our analysis algorithms are resilient to most types of dependency injection, where as long as let's see, we have a call site, right, and it could be any of these functions. If we don't have an application configuration, we're typically still able to look at the type and consider what if it went into this one, what if it went into this one, what if it went into these candidates. Sometimes, if you had maybe multiple implementations available, we might actually report the defect 3 different times if it actually exists in all of them. But we'll play that out. So to answer your question, we support Spring. We support a couple other common dependency injection frameworks. If it is something else, we can usually infer what is, as long as the target was compiled, we can usually figure it out automatically. In the back. Yes. Of course. So the traditional, Coverity commercial software, You download the analysis software, you run it on premise. It integrates into Jenkins, integrates into pretty much you name it. Honestly, I think the integration is pretty easy. The defects are really the exciting part for me as a developer. Good question. This is, as I've mentioned, this is a very, oh, sorry, the question was, how fast does that run compared to, say, FindBugs? So first, let me set some background. FindBugs does a bytecode analysis, which is actually very fast. It's like analyzing the machine code, the JVM code, to look for defects. Whereas we have to actually parse the code, generate an AST, run a very heavyweight analysis. So it is slower than FindBugs. I think our marketing material says 7 million lines of code per hour, which is obviously it's actually much slower than FindBugs. But there's an important detail here. The way most of our users run Coverity is they run it kind of on the server on a nightly basis. That analyzes the entire application. But when you just make a change, typically a change set is what, like 5 files, 10 files. When we analyze those individual files, that comes down to seconds per file. We do an incremental. Well, it's more than incremental. We analyze the whole program, and then when we analyze your change, we really just analyze those changes. And let's say your change makes a call into something that you didn't change. What we do is we just pull in the information from the full analysis. So that takes it down to, maybe 5-10 seconds per file, or maybe a minute for an average change. That tends to be, that's really necessary in order to run this inside the IDE. Right? This isn't spell check as you type, but personally I think that's the wrong approach. Right? How do I know if I have a defect that spans 2 files and I save one but I'm not done with the other? How do I know it's ready to analyze yet? Sorry, that was a digression. Any other questions? Yes?
Any other languages in the JVM?
Very good question. That's actually been a hot one this week. So today we only support Java. We do, and that's due to our analysis of the Java source code itself. In order for us to support Scala or Groovy or some of these other languages, that's something that we're looking at, but we'll have to build a new analysis engine for that. So that's not going to happen tomorrow. I am curious though. Can you tell me like how much, what percentage of your code is usually Java versus these other languages?
Well, professionally, it's mainly Java.
Uh-huh.
We have a personal interest in Scala.
Okay, cool. Scala's probably the number one that I've heard lately.
If we're running it on premises,
Mm-hmm.
then would it be doing its thing on the machine that was doing the build, or would it be doing similar to what you were saying, just collecting it locally and then sending it to your server?
Good question. So the question was, when installed on premise, kind of does it still work like a cloud where you do a build and submit to another machine for analysis? Typically, we run the analysis on the same machine that ran the build. There's no reason for that. That's just the way most people set it up. It's certainly possible to run the build on one machine and then copy the data to another computer to run the analysis. That happens with some of our users where they cannot afford to increase their build time. Right? Maybe the build just has to complete within a certain amount of time, so they can't introduce any latency, so they just copy it somewhere else and run the analysis there. But frankly, the analysis is generally fast enough that that is not a problem for most cases.
You must be knowing the top 10, top 100 common patterns, common bugs to find in the
Mm-hmm.
So talk to Oracle.
Mm-hmm.
Any dialogue between you and Oracle. And basically, those top 10 can be adjusted into their compiler.
Mm-hmm. So that's a good question. We are actually, it's actually just recently that we've become friendly with the Oracle, the Java Platform Product Management team. I've actually myself had a few meetings within the last few months. They're looking at, Oracle is actually, I'm not sure the proposal numbers, but there are some proposals on the table to start bringing static analysis more into the Java compiler itself. What we're finding, though, is that the types of defects we report are beyond the scope of compile time. I mean, the detection, not just the detection, but the reasoning that's required to weed out false positives is CPU intensive enough that it's just not affordable to put into the compiler itself. But we are definitely talking with them about there are certain rules that might make sense to include. But what's more interesting to me, anyway, is how can we evolve the Java compiler APIs and languages to build Coverity more closely in. The way Coverity works today, this is a bit of a tangent, but you have to run the Java C, and then you run the Coverity compiler. This would be much more efficient if you could just run the Java C, and we could plug into that. And like as the compiler runs, we generate everything we need for analysis. And then we run the analysis asynchronously. Another question? So I'm out of time, but I'm just going to squeeze this one in. The question was, have we run into a hit because of Java 8? So Java 8 was released in it was public and it was final in March. We have not hit any performance problems with Java 8. For Java 8, it's just been a matter of really brute force for us adding support for analysis of lambdas, for adding support for all these things. It hasn't really, I haven't seen a analysis time impact. Okay, I promise I'm done. Thank you.